Alright, hello everyone and welcome to Lab 3 of our Organic Chemistry Lab series that is online this semester. This week we'll be covering the isolation of eugenol from allspice. So eugenol is this molecule here, and it's found in allspice, which are little berries you may have used in cooking. So this overview goes over the techniques that are going to be used in the lab. So the purpose is to isolate the eugenol from the spice, allspice, using steam distillation, which the apparatus is here, and liquid extraction, which is what this separatory funnel symbolizes. So let's move on and discuss what exactly allspice is and what eugenol is. And you can see that eugenol is pictured right here. Now eugenol is a molecule that falls into a subclass of molecules called vanilloids. Now vanilloids have this benzene ring, they have this O-methyl group, and then they have this OH group. And here they have an R group, and the R group is the variable, so it can change. But this is what remains common throughout the entire vanilloid subfamily. So the prototypical vanilloid here is vanillin. So vanillin is a molecule which comes from vanilla beans. In ginger, you have gingerol, and then eugenol here, which is the one we're using, comes from allspice, but it can also be found in cloves and cinnamon sticks. Some other common ones you may have heard, capsaicin is found in chili peppers, so that's what makes them spicy. And in cumin seed, there's curcumin. So you can see that all of these share the same benzene ring with the O-methyl and OH group. Now all of these vanilloids fall into a greater class of molecules called natural products. And a natural product is a molecule that's produced by a living organism. So a lot of these have biological significance because they come from nature, which turns out why we can taste them, why we can smell them, and why they're useful in cooking. So let's discuss some of the properties of these molecules, and first we'd like to discuss solubility. Alright, so in terms of solubility, you may have heard this phrase in general chemistry, which is like dissolves like. So I've created this table here which describes the differences between polar molecules and nonpolar molecules. So polar molecules are often called hydrophilic or water-loving, and nonpolar molecules are often called lipophilic or fat-loving. So in terms of functional groups, the functional groups that polar molecules tend to have are OH and NH, and they have less CH bonding. But for lipophilic molecules, they tend to have less OH and NH bonds, but they have more CH bonds. So to put this into perspective, an example of a nonpolar molecule was, as we previously discussed, eugenol. So you can see that it only has one OH bond here and it has very many CH bonds. Now in contrast, the typical example given for a polar molecule is water. So if you have a water molecule, it has two OH bonds, but that's kind of straightforward. An organic example would be something like perhaps ethylene glycol. So if we have a molecule like this, you can see that it has two OH bonds, but it only has four CH bonds. So it's not in terms of, we're not really concerned about counting how many of each it has. It's more of a qualitative understanding of, well, this molecule has less OH bonds and this molecule has more OH bonds, and this influences what they're going to be soluble in. So polar molecules like these will be soluble in water, so water is soluble in water, but this molecule ethylene glycol is actually found in antifreeze and it's mixed with water to put in our car engines, and something like eugenol is obviously not soluble in water, and that's something we're going to take advantage to isolate the molecule using steam distillation. So steam distillation is sort of similar to the technique we used in the first lab, but the difference being it's used to isolate temperature-sensitive compounds that are immiscible with water. And immiscible is a term that describes substances that do not mix when they come into contact with each other. So for example, if you mix oil and water, they will separate into different layers. So eugenol, the molecule we discussed, qualifies as a candidate for simple distillation because, one, it is temperature sensitive. The boiling point of eugenol is about 254 degrees Celsius, which is almost 3 times as much as the boiling point of water. And it's also immiscible with water. So if we took a pure sample of eugenol and mixed it with water, it would separate into a different layer. So if we tried to distill eugenol straight from the allspice without adding any water, we would have to heat it to this temperature, and by that temperature the eugenol molecule might decompose, and obviously we wouldn't want that because it would no longer be eugenol. So we take advantage of this apparatus, which is a steam distillation apparatus, and we fill this chamber or this boiling flask with a little bit of water, And what the water does is it acts as a carrier vapor that pushes the eugenol out of the water, or out of the allspice, and up into the condenser and into our collecting vessel, which in this case is displayed as a grad cylinder. Now the purpose of this Claisen head here, normally it's used to add a separate neck to a flask that only has one neck, but the purpose here is to increase the head space above the boiling mixture to prevent foaming. So hopefully in the experiment this extra space will prevent foaming, which could contaminate the distillate collected here. And this right here is a separatory funnel, which will be used to periodically add water, because we want to keep the amount of water within the flask constant. So this describes the simple distillation, or excuse me, the steam distillation apparatus. So once we've collected our distillate will be a mixture of both water and eugenol. So we're going to have to get it out of there somehow, because we just want the eugenol and none of the water. So in order to do that, we're going to have to discuss a new technique which is widely used in organic chemistry called liquid-liquid extraction. So liquid-liquid extraction is the separation of compounds based on their solubility in two immiscible liquids. And to describe this, let's use our example. So say we have our distillate, and our distillate will consist of primarily water. So say this is our water layer here, and it's going to have several molecules of eugenol in it. And we're going to mix this. So we have a polar liquid here, which is water, and we're going to mix it with a non-polar organic liquid, which it will be, I'll symbolize it using this pen here. That substance will be called dichloromethane. Now this substance has a density that is above 1.0 grams per milliliter. And that means that the dichloromethane will be on the bottom, because when you put two immiscible liquids into the same vessel, the less dense liquid will be on the top and the more dense liquid will be on the bottom. So water has a density of about 1.0 grams per milliliter. So it's going to be up in the upper layer, but the dichloromethane will be in the bottom layer. Now when we mix these two liquids together, because the eugenol is more nonpolar, it will migrate from the water into the dichloromethane. So now that we've separated the eugenol from the water, we can now somehow remove this layer and then evaporate the dichloromethane. Now this is obviously in a beaker right now, so it's not that convenient to do. So we can take advantage of that by using this piece of glassware, and this piece of glassware is called a separatory funnel, and it is made to separate these two layers. So let's just symbolize that we have our water layer on the top once again. So here is our water layer. And then our bottom layer here, excuse me, is going to be our dichloromethane. So the eugenol is in the dichloromethane layer, which can be drained out the bottom via this stopcock. Now, the issue comes here is how many times do we extract? How many times do we add dichloromethane and drain off the layer? Well, if we were to do one extraction, we wouldn't get all of it, and here's why. There is an equilibrium of how much eugenol exists in the water layer and how much eugenol exists in the dichloromethane layer. And typically it's around 90%. So say for example, we perform our extraction, we add our dichloromethane, this layer will consist of about 90% of the eugenol we started with, and this will consist of about 10%. So if we just did one extraction and we only have this layer of dichloromethane, then we're not going to get all of it. So what we do is we drain out this lower layer and then we add fresh dichloromethane. So we have our water layer, which is the same. We add some fresh dichloromethane, and now we're going to end up having 90% extraction again. So we're going to get 90% of the remaining 10%. So we're going to end up with basically a 99% mixture now, and now a 1% mixture, or 1% eugenol remaining in the water layer now. Now, in order to make sure we get absolutely as much of it as possible, we can repeat this step once more. Okay, and add some fresh dichloromethane a third time. And this will mean that we get 99.9% of it and there will only be about 0.1% eugenol left in the water layer, which is probably negligible. So this is why it's always more important to do multiple extractions using a smaller amount of solvent than one big extraction. So if this is all a little confusing about how this process works, it'll be more visually explained in the experimental section. So the final thing I wanted to mention is once we have our dichloromethane extracts, what we want to do is we want to put them into an Erlenmeyer flask, or they'll be collected in an Erlenmeyer flask. And the issue is, although we separated it from water, there's still going to be some water molecules within our DCM extract. So this is our DCM extract, but there's still going to be a little bit of residual water in there. Now to remove that water, which I'll symbolize by maybe putting a few dots, blue dots in here, is we're going to add a compound called anhydrous sodium sulfate into the flask. And sodium sulfate, Na2SO4, is a salt that forms a complex with water. In fact, for every 1 molecule of sodium sulfate, it can bind 10 molecules of water. So we're going to add this salt to the dichloromethane, and by the way, because sodium sulfate is a polar, in fact it's an ionic compound, it won't dissolve in a non-polar substance like dichloromethane, but it will absorb the water. So once it's absorbed the water, so let's say we add our sodium sulfate, the sodium sulfate will settle to the bottom with all the absorbed water, and then we can decant and filter off the dichloromethane. So once that's accomplished, we can take our dichloromethane and put it onto a rotary evaporator and figure out how much eugenol we have. Now, the final calculation for your worksheets to figure out how much eugenol we recovered can be found by calculating the percent recovery. So the percent recovery equals the amount of eugenol we collected from this extraction, from this entire process, divided by our starting amount of allspice. So in this case, it's going to be 60 grams of allspice times 100. So it's very similar to percent yield, but because we're doing an extraction and not necessarily a reaction, it's called percent recovery. So we can use this calculation to figure out how much eugenol we recovered. Okay, we'll see you in the experimental section. Alright, so we have our 60 grams of allspice here, which contains our eugenol, and we need to add it to this flask, which is our boiling flask. So we'll take a powder funnel, just kind of stick it in there, and dump in the eugenol. Now this process can be a little tricky because the eugenol is fine, but with the spatula, we can get it all in. So scrape, scrape, scrape. So normally in this lab, students would use 15 grams, but because the second part of the lab, 4 students will usually combine their products. So in this case, because it's only just one of us here, we're going to use 4 times the amount, a total of 60 grams, so that's most of it. Now we're going to add 250 milliliters of water on top of that. The exact quantity is not important. So we'll add a little bit and make sure we don't overfill the flask. So you can see already it's quite a bit. Kind of looks like coffee grounds in water. And we'll swirl it around just to make sure all the eugenol, or excuse me, make sure all the allspice is coated and wetted by the water. And I think we're gonna stick it at that. So we added about 200 mils. Maybe we'll add a little bit more. In fact, we want to wash the sides down here, make sure it's not on the joint. There we go. Maybe add a little bit here. And the spill is no big deal, just a little bit of water. Okay, so in fact, let me just wipe this down a little bit, the flask. We've got our allspice and water in here. We'll place it into the apparatus. So this is our heating mantle, which is going to heat the mixture. Then on top of that, we'll put a Claisen head. So normally this piece of glass is used to put basically 2 necks on a single neck flask. So because this is a 3-neck flask, it's not really needed in that purpose. But the purpose of this is to basically increase the head space because this mixture likes to foam. So if it does foam, this gives us a little bit of breathing room so the foam will not slide over into the condenser and down into our distillate. So on top of that, we place our still head, and we can add the condenser here, and we can clip it in place. Then we can seal it up, so place some stoppers here. And then here, on this piece of glassware, we'll place our separatory funnel. And the purpose here is to function not really to separate compounds, but as a way to add water to the reaction, or to the distillation as it's going. And the purpose of this is we want to keep the amount of water in here constant. So by dripping water, we can compensate for the amount of water that's lost through the distillation. So now that everything is assembled, we're good to go. And we can turn on the heat and wait for it to boil. Alright, so it's been about 10-15 minutes and our mixture has begun to boil, and as you can see, it is threatening to foam up a little bit. Some of the allspice has climbed the glass, but thanks to the Claisen head, we're probably not going to get a foam over, thankfully. So as you can see, the distillate is not perfectly clear like you would see with normal water. It's a little murky, and in the distillate here, where we'll be collecting it in the graduated cylinder, we'll be able to see what the distillate looks like, and you'll notice it's not just regular water. It's going to look a little bit different in appearance. So we'll come back when we collect enough distillate. Well, you can see that we've heated it and now it's beginning to boil vigorously, and you can see that it's threatening to kind of foam up and contaminate our distillate. But thankfully, because we have this extra room, because of the Claisen head here, we have some breathing room, so hopefully throughout the distillation this bubbling will not climb into the condenser. If you look here, you can see that we're dripping at a somewhat slow pace. So we've collected maybe about 10 mils of distillate thus far, and it's a very milky distillate because as you know from our pre-lab workshop, the eugenol is immiscible with water, so they do not dissolve in each other, and that's why it's forming the milky appearance. So to compensate for the water in the distillate, we want to keep the amount of water in this flask constant. We're going to open up the sep funnel here to drip just a little bit periodically. So it's kind of difficult to see, but maybe if you look right here, you can see a little bit of dripping from the sep funnel, which will help it boil. So we'll see you when we've collected all the distillate. Alright, here's an update. So our attempts to stop the boiling flask from foaming up did not work, and as you can see in our distillate, a little bit of foam and allspice made it over, which is why it looks a little brown. And to fix that problem, we have basically transferred the boiling mixture of allspice and water to a bigger flask, and our foaming problem is now under control. So this apparatus is, for the most part, essentially the same. You have a boiling flask here, a still head, and a very long condenser, and we are now getting distillate at a very fast pace. We were really struggling to collect distillate at a fast pace, but now we've got enough. And perhaps in half an hour, we will be done. So we've been distilling for perhaps an hour and a half here, and you can see the water level has dropped substantially, but we know the distillation is pretty much complete, because if you look at the distillate dripping here, you can see that it's no longer milky, which tells us that there's no more eugenol coming over. It's mostly just water. So the original fraction here is very milky. It contains a lot of eugenol in it, but what we're collecting now has very little. So we can stop the distillation and move on to the next step. Alright, so we've got our distillate from the steam distillation, and as you can see, it's fairly milky because it has both eugenol and water in it. So now we're going to commence with the liquid extraction portion of it. So this is our separatory funnel, which is, by the way, my favorite piece of glassware. It's basically a gravy separator. So at Thanksgiving, you have a little cup basically with a spout, and it'll separate the gravy, the fat, turkey fat, from the liquid portion of it. So this is a device that does the same thing, only it's made of glass. So we have our sep funnel. This is the stopcock. So when the stopcock is like this, vertical, the hole here is aligned with the stem and the liquid can flow out. So it's always important that you have to keep this closed when you pour liquids in, or else stuff will fall out. That's a rookie mistake, don't do it. So we have our distillate, which we will transfer to the separatory funnel. And I think what we will do is we will do 3 extractions with about 40 mils of dichloromethane. But the exact value is also not that concerning, so we'll just roughly measure 40 mils. And we can rinse out our distillate flask to try to get all of the eugenol out, so give that a little shake. Okay, and then we'll put this, and you'll see that when I add this DCM, because the DCM is more dense than water, it'll go towards the bottom, and it will form a separate layer. Okay, so you can see the 2 layers have formed. On the top is the water with the eugenol, and on the bottom is the DCM. So here at the inner phase, you can see where the 2 phases meet. And you can see some maybe dichloromethane trying to get to the bottom. Now, the next step is, if we just left this here, there wouldn't be very good extraction. So we need to agitate the solution in order for the extraction to proceed. So we're going to cap the separatory funnel. And a lot of students think this is the most entertaining portion of the lab because it's most interactive, it's physical. So you have to get a firm grip on the stopper because you don't want it to leak. So I'll put a firm grip here, and this hand will not move. So I'll raise it out of the ring and invert it. Now the first thing I'll do is I'll vent it. And you didn't hear anything. And it's important to vent the separatory funnel because when you shake it, there's going to be a lot of pressure built up, and you need to relieve that pressure. Sometimes if there's too much pressure, the solvent could leak from the joint up here, or it could leak from the stopcock. So we'll close it and shake and vent. So we'll shake it and vent. So you just heard a lot of pressure build up. We'll do it again. And vent. We'll do it a 3rd time. Now when you vent, it's important to point it into the hood. So if you were in the lab, you wouldn't want to point it to your buddy and do it. So always point it into the hood. And the magic rule in separation is kind of like the rule of 3. So you shake 3 times and you vent 3 times, and then we're going to extract 3 times. So 3 is kind of a magic number. So there's a little bit in the stem, so I'll open it up here to try to get it to come back in. It might not separate. Now if you shake too vigorously, you might get an emulsion, which hopefully we don't have here. So let's find out. So let's see. So you can see we have a little bit of an emulsion here. So you can see I shook it pretty hard. I like to shake it hard. I like to live dangerously. And we have a little bit of an emulsion, so the layers where they separate is not very clear. So to resolve that, we're going to add some brine. Alright, so we're back. We've got some brine. So brine is basically a solution of saturated salt water, so sodium chloride and water. And what it does is it kind of forces the water bubbles to come back into the water layer instead of hanging out in the DCM layer. And sometimes this works very well and sometimes it doesn't, so I guess we're going to find out here. So we'll add a little bit. Maybe we'll give it a little bit of a swirl here. I think I will invert it, try to coax the water back into its layer. Well, I think it helped a little bit, but it's still kind of bubbly there. Another thing you can do is you can try to drain it away, and sometimes it resolves itself. So let's just try draining it away. Now, what we've done is, so we've performed our first extraction. Most of the eugenol now, 90%, should be in this DCM layer. So the eugenol has moved from the water layer into the DCM layer, and we want the DCM layer because it contains the eugenol. So let's try to remove some here. Okay, so let's try to give it another swirl. Sometimes if you swirl it, the bubbles come back to their layer, so put the cap on so I don't spill any. Nope, didn't seem to work. That's all right. Let's just go on to the next extraction and try to get the layers resolved again. So maybe we'll add a little more DCM this time. Let's add maybe closer to 50 mils. That might form the layer a little bit better. And once again, we can rinse out the flask which contained the distillate, try to get all the eugenol out. Yeah, and you can see that the layers have kind of separated out a little bit now that I've added more DCM. So what I'll do is I'll try to shake it a little more gingerly this time so as not to emulsify it. So okay. And slowly you can see the bubbles resolving, so I think this time it'll look a little bit better. Yep, you can see. So if we give it a few minutes, perhaps the layers will resolve perfectly this time. It's taking a little longer than I'd like. Let's add a little more brine here. Alright, so we've waited a few minutes, and as you can see, the emulsion sort of resolved itself with a little more coaxing. So we can drain our second DCM extract into our collection flask. Now it's important to not drain it with the stopper in place, because if the stopper is in place, it won't drain quickly because it'll form a vacuum in here. So when you drain, always remove the top stopper. And now we can drain the dichloromethane. Okay, so maybe we can try to swirl it a little bit to try to get that last bit of emulsion resolved here. Yeah, so you can kind of see where the interface is here, but you know, some of the water just doesn't want to go back to the water layer, so that's why we see some bubbles in here. So what we can do is just add the rest of the DCM that we're going to add, just like before. So we'll just tolerate that little bit of excess. So add a little bit more. Oh, actually, let's rinse the distillate flask again. Okay, so this is our third time, our last time, so we take it out, and once again we shake and vent. So let's shake it a bit, vent it. Okay. And here you can see the interface, so this is where it should be. Of course, there's still a little bit of an emulsion here. I think we'll add a little more brine. And we'll take this pipette to try to agitate the bubbles, kind of coax them back into their own layer. Okay, you can see that we've resolved our emulsion fairly well. There's still a little bit on the side, so let's drain off the DCM layer. So now that the interface is approaching the top of the stopcock, we can slow it down a little bit and be a little more careful. So you want to try to avoid getting as much water into the flask as possible. So I stopped it right there. We can try to maybe swirl it just a little bit more. Maybe it might resolve, it might not. I will try to invert it. Maybe that will resolve it. There we go. So I think we got, oh, there's some bubbles. Try again. Perhaps I'll try the pipette trick one more time. If it doesn't work, that's okay. We've got the majority of the eugenol out of there. Yeah, maybe we can drain a little bit more. So. And that's as much as I'm willing to risk here. So we've got our 3 DCM extracts combined in this flask, and as you can see, there is, maybe you can see or maybe not, but there are a few bubbles of water floating in there, and they're visible because of our emulsion problem here. We didn't perfectly separate the layers, and inevitably there's always going to be a little bit of water in the dichloromethane. So to resolve that, we have our anhydrous sodium sulfate, and we're going to add some here. Now students always ask how much to add, and the trick is to start with a little bit. Oops, let me add a little more, because there's quite a bit of water in there. And swirl it around. Now when the solution is dry, the liquid will look very clear, crystal clear, and the sodium sulfate will not be clumped together, so it'll kind of look like a snow globe with their little particles flying around, but you can see most of it has clumped up and sank to the bottom. So I think we need a little bit more here. So, oops, this bottle is being a little stubborn. I think we should add a little bit more. There we go. That should do it, so let's swirl it again. Yeah, now this looks much better. So you can see when I swirl it, there are small particles of sodium sulfate flying around, so it's no longer clumping. And the solution is crystal clear. So now that we have a dry solution, which means it's free of water, we can take our flask. So I've written the weight of the flask right here, so it's 97.28 grams. Now we can take a funnel and some cotton, and we can filter the mixture. Now there might be a little bit challenging because this thing might form a seal, so I'll lift it out a little bit. And we're going to filter the sodium sulfate away. Oops, see, it's being a little hesitant there. So pardon us while we get a separate funnel. This one seems a little too big. Alright, so we've got our new funnel here. This one should work a little bit better. And we've just replaced the cotton, so we've put the piece of cotton into this funnel, and we can continue with the filtration. Okay, now it's always good practice to rinse out the previous vessel to make sure you get all of it. So there's still a little bit of eugenol and DCM in here, so we'll rinse it out with a little DCM too. So I'll shake this around. Okay, now I'll do a few more times. Okay, so now we have our crystal clear solution. There's no sodium sulfate in it, and there's no water, so it just has DCM and eugenol. So now we just have to remove the dichloromethane on the rotovap. Alright, so this is the rotovap, which stands for rotary evaporator, and this is what this entire apparatus is, so let's go through it. So a rotary evaporator is basically a glorified distillation apparatus, a glorified vacuum distillation apparatus. So in here, in this water bath will provide the heat instead of a heating mantle, and inside the rotovap, or inside this water bath, will be the flask with the solvent that needs to be removed. I don't have it now, but it'll be hooked up to this joint here. Now, this joint is a bump trap, and we'll cover that in a little bit, but we have our heating, boiling mixture here, and then it's going to be connected to this condenser here. So this condenser has cold acetone, which is chilled by this chiller here. And it's going to vaporize all of the solvent here, travel up this steam tube, and hit the condenser and fall into the solvent trap here. And when we turn on the rotation, maybe you can see, it'll rotate our flask. And vacuum is provided by this vacuum pump, and you can control the strength of the vacuum using this needle valve. And you can read the vacuum using this pressure gauge up here. Now, the important thing is, let me see if I can grab the flask here. Now, the flask is a little bit above half full, so sometimes on the rotovap you have your flask. Sometimes what will happen is there's called a bump, and a bump is when the solvent flash boils and basically shoots the liquid this way into the rotovap. Now, this is the bump trap, which you can see by its design. Maybe I'll rotate it. Oops, maybe too much, but it's designed to not allow the liquid to jump into the solvent trap, which would contaminate it. So to prevent bumping, the first thing is you rotate it, so that helps mix the solvent evenly so it evaporates smoothly. But the other technique is to fill the flask no more than halfway full. As you can see, this is fairly full, so there might be an increased risk of bumping, but that's okay. As I said, some people just like to live dangerously, and I am one of those persons. Alright, so we've got our flask, and we're going to put it onto the rotovap. Okay, and we'll put a blue keck clip to make sure it doesn't fall into the water bath. That's a very common problem, in which case you pretty much lose all your product, which is a shame. The chiller, you can see I've taken out of the chiller because the chiller when it's on is kind of loud, so I've just filled the condenser with very cold acetone. So it functions the same. It's just a very cold surface for the solvent to condense on. So we'll begin our rotation here. So you can see the flask is turning. And we're going to turn on the vacuum. Now, right now the vacuum gauge is at 0, and that is because the vacuum is not connected to the glass apparatus. So to do that, we're going to rotate this, we're going to rotate this piece of glass this way. And we're going to, let's see, oh, maybe it's not forming a good seal. Here we go. All right, and as you can see, the vacuum is slowly increasing. Okay, we can increase the vacuum a little bit. And already you can see some of the vapor is making its way up the bump trap. And this is kind of remarkable. So the boiling point of dichloromethane is around 40 degrees Celsius, but the temperature of the water bath is somewhere around room temperature. It's probably no more than 30 or 35 degrees Celsius. So, and the way we're able to boil the DCM or remove the DCM below its boiling point is because this vacuum pump reduces the external pressure. So if you remember to our first lab when we talked about boiling. So boiling is when a liquid's vapor pressure equals the atmospheric pressure. So the two different ways of getting a liquid to boil is to either increase its internal temperature, or you can decrease the external pressure, and that's what this apparatus does. So we decrease the external pressure almost to a full vacuum if you wanted to, so we can remove these solvents at low temperatures. And that's good because especially when you have temperature sensitive compounds, you want to remove them at a low enough temperature so as not to destroy your compound. So this will be over in about a few minutes. So if you can see, we've removed the majority of the DCM. In the flask here is just a thin coat of what is probably the eugenol oil. So to make sure most of the DCM is gone, we'll leave the flask on the rotovap for a few more minutes, which will remove the remainder of the DCM, and then we'll have our eugenol oil left in this flask. Alright, so we've left it on the rotovap for a few minutes, so now we can turn off the vacuum pump. So that'll hopefully make it a little less loud, and we can open up the apparatus to the atmosphere, which will vent it, and then now we can take the flask off the rotovap. And now you can see that we just have a little, oh, let me wipe the bottom of it. We have a slightly yellow runny oil, which is hopefully our eugenol. So we'll dry off the outside of the flask and put it on the balance, and we'll figure out how much we got. So we've got our flask full of eugenol on our balance here, and the mass it's giving us is 98.52, and we'll subtract that from the mass of the flask, which was 97.28, which gives us a final mass of 1.24 grams. So that's how much eugenol we got from this experiment, and we'll use that in next week's lab to methylate it and do our biological activity. And if we smell this, yep, it smells like Christmas in a flask. It always makes the lab smell good. So we'll see you all next week. Calculate your percent recoveries from that mass, and we'll see ya.